What if everything you've ever touched, seen, or felt wasn't real, not in the way you think? What if our entire universe was a hologram? This isn't a scene from science fiction. This is real theoretical physics. A growing body of scientists now seriously consider the possibility that our three-dimensional world, with its galaxies and stars and endless space, is merely a projection from a distant two-dimensional boundary we can't even perceive. So what does that mean? Could your life just be the illusion of depth in a flat cosmos? If reality is a projection, then what is projecting it? And if space itself is an illusion, does time even exist the way we think? This idea might sound outlandish, but the deeper we peer into black holes, quantum mechanics, and information theory, the more this impossible truth seems likely. We're about to explore a theory so wild it bends our minds backwards. But I promise, this isn't chaos. This is elegant physics, with just enough mystery to keep your thoughts floating as you fall asleep. Close your eyes. Imagine everything around you. This room, the planet, the stars above, compressed into a two-dimensional sheet. It still exists, but its depth is an illusion. Like a hologram on your credit card, it looks 3D, but the information lives on a flat surface. This is the heart of the holographic principle, and it didn't come from wild speculation. It came from the study of black holes. In the 1970s, physicist Jacob Bekenstein made a strange discovery. When a black hole swallows matter, the amount of information it holds doesn't scale with volume, like you might expect. It scales with surface area. That's odd. It's like saying the contents of your refrigerator are determined by the size of the fridge door, not the shelves inside. Later, Stephen Hawking's work on black hole radiation confirmed this bizarre truth. Black holes leak information, and their entropy is tied to their outer surface, not their inner mass. And then, in 1997, theoretical physicist Juan Maldacena proposed a mind-breaking idea. A universe with gravity, like ours, might be fully described by a simpler universe on its boundary, without gravity at all. This became known as the ADS-CFT correspondence, and it cracked the door open to a terrifying implication. Our universe might be holographic. If the universe is holographic, then everything inside it, your body, your memories, your entire sense of here, could be encoded on a distant boundary we can't see. Just as a 2D DVD holds the full story of a 3D movie, this distant edge could contain all the data that gives rise to our world. That means your 3D experience is emergent, not fundamental. Matter might not be matter. Space might not be space. Reality might be compression. You've probably heard of simulation theory, the idea that we're living in a computer program. The holographic universe is stranger, because in this view there's no programmer, no digital matrix, no laboratory, just physics, just information, encoded in patterns beyond our reach. It's not a digital simulation, it's a mathematical mirage, and this might explain something even more mysterious. In quantum mechanics, particles can be entangled, meaning one particle knows what happens to the other, even across great distances. That shouldn't be possible if space is real. But if space is an illusion, just a projected phenomenon, then there's no real distance to separate the particles. They're not far apart, because far doesn't exist the way we think. In a holographic universe, quantum entanglement makes more sense. So do black holes. So do cosmic limits on information. And suddenly, everything fits. Here's the weirdest part. You may never perceive this holographic boundary. It might be at the edge of the known universe, or inside black holes, or hidden in the cosmic microwave background. But wherever it is, it's likely that everything we see is just a shadow of the information stored there. Plato once spoke of a cave, where people saw only shadows on the wall and believed them to be real. Modern physicists are now suggesting we might be living in a version of that cave. If the holographic theory is true, and future experiments confirm it, then we'll need to rewrite the very foundations of physics. Gravity, time, energy, matter, all may be emergent from something deeper, something informational. It doesn't mean the world is fake. It means it's stranger than we ever imagined. A hologram isn't a lie. It's a real projection from a real source, just not the one we thought. And maybe, just maybe, consciousness itself plays a role in interpreting that projection. Now, let that thought linger as you drift further. Because the next theory is even stranger. What if gravity itself doesn't exist the way we think? What if it's just entropy in disguise? Let's explore the idea of entropic gravity, where space bends not because it must, but because it wants to. You were taught that gravity pulls, apples fall, planets orbit. You stay grounded because a force holds you down. But what if that force doesn't exist? What if gravity isn't a pull at all, but a push? Not a force, but an illusion, a side effect, a ripple in something deeper. This is the quiet, radical idea behind entropic gravity. To understand it, you need to let go of everything you thought you knew about how the universe works. Let's begin not with a planet, but with a probability. Imagine a grain of sand sitting on the surface of a giant sphere. There's no gravity in this picture, only statistics. The sand moves, not because it's being pulled, but because the universe wants to maximize disorder. In physics, that disorder is called entropy. And the universe, it seems, has a preference, a desire, a built-in drive to increase entropy wherever possible. This idea forms the heart of one of the most radical proposals in theoretical physics today. That gravity is emergent, not fundamental. Not one of the four forces, but a statistical consequence of microscopic information rearranging itself. Let's rewind. In 2010, Dutch theoretical physicist Erik Verlinde shook the physics world by suggesting a new view of gravity. He proposed that gravity isn't a basic building block like electromagnetism or the strong force. Instead, it arises from something more abstract: information. Here's the key insight. Think of matter like a planet, not as a thing, but as stored information. And space, that's just a medium where this information is encoded. Now imagine that when information rearranges in space, it creates an imbalance, a pressure, a statistical gradient that tries to even itself out. This gradient, this urge to spread and balance, is what we perceive as gravity. In Verlinde's model, gravity doesn't pull things. It emerges because systems move toward higher entropy, more disorder, more possibilities. Think of how a drop of ink spreads in water, not because anything pushes it, but because that's the most statistically likely outcome. In the same way, matter falls toward other matter, not because of some invisible tether, but because that's the most probable way to organize the universe's information. It's not Newton's falling apple. It's entropy's inevitable dance. This might sound abstract, but here's where it gets even more profound. If gravity is entropic, if it arises from information, then space and time themselves might not be fundamental either. They could be emergent properties, illusions formed by the interactions of more basic, microscopic units, bits of data dancing in dimensions we can't see. And if space and time are illusions, then everything we know, distance, motion, causality, might just be shadows of something deeper. This idea aligns strangely well with the holographic universe we discussed before, because both theories say what we experience isn't the source, it's the consequence. Verlinde's theory also sheds new light on dark matter. For decades, physicists have noticed something strange. Galaxies spin too fast. According to Newton and Einstein, they should fly apart. To explain this, we invented a placeholder, dark matter, an invisible mass that holds galaxies together. But what if we don't need dark matter at all? What if our equations are wrong, not because something is missing, but because gravity doesn't behave the way we thought? Entropic gravity offers a compelling explanation. If gravity is emergent, its behavior might subtly shift on cosmic scales. It would appear stronger or weaker depending on the entropy gradient, not just mass. Verlinde's equations match galaxy rotation curves without needing extra, invisible mass. No dark matter, just a new understanding of what gravity is. Of course, this theory is still controversial. Not everyone agrees. It hasn't yet fully explained all cosmological observations, but it's gained attention because it does something rare. It simplifies. It connects gravity to thermodynamics, to information, to entropy, and in doing so, it hints at a unifying principle across physics. Here's a strange metaphor. Imagine the universe as a giant library. Each book is a particle. Each shelf is a field of energy. Now imagine the library rearranges itself to keep things messy, to maximize the ways it can be read. That shifting, those movements of books and shelves, is what we call forces. But really, it's just the library doing what it always does, spreading information. Gravity, then, is not a thing. It's a story that emerges when enough information organizes itself across enough space. And if that's true, then the world feels a little different, more fluid, less mechanical, less about objects and more about patterns. It makes you wonder, if gravity is just information, then what are we? Are our thoughts patterns too? Are we walking gradients of entropy? The idea that gravity could be emergent changes more than just equations. It changes how we think about ourselves. We're not just living in space, we're participating in it. Every thought, every breath, every falling object. It's all part of the great balancing act of information. And maybe, when we look up at the stars, we're not looking at distant objects being pulled across space. Maybe we're looking at ripples in a fabric of probability, statistical whispers, entropy's quiet logic. And now that gravity has shifted beneath your feet, it's time to let your thoughts drift into the next mystery. Because next, we'll explore an even stranger idea, that your consciousness itself might be quantum. What if your mind isn't just a byproduct of the brain? What if consciousness itself is woven into the quantum structure of the universe? Not thoughts from neurons, but thoughts from quantum vibrations, echoing in the microarchitecture of your brain. This is the theory of orchestrated objective reduction, Orch-OR for short. It's one of the most controversial and fascinating theories in modern science, and it begins not with psychology, but with physics. The mystery starts with the mind itself. You think, you feel, you imagine, but where does that awareness come from? How do clumps of matter, biological and wet, produce the vivid richness of a conscious moment? This is what scientists call the hard problem of consciousness, and so far, no classical theory can explain it, because consciousness doesn't just process data, it experiences it. Now imagine for a moment that this experience doesn't emerge from chemistry at all, but from the strange, shimmering probabilities of quantum mechanics. Roger Penrose, a mathematical physicist, believed that the laws of physics, especially gravity, might play a role in consciousness. He suggested that something in quantum mechanics was missing, that the collapse of a quantum state, when possibilities become actual, was not random, that it happened for a reason, and that reason involved a kind of self-awareness embedded in space-time. But how could this relate to the brain? That's where anesthesiologist Stuart Hameroff enters the picture. Hameroff had been studying tiny structures inside neurons called microtubules. These are cylindrical protein lattices, so small, so intricate, that they were often ignored. But Hameroff saw something special in them. Microtubules weren't just scaffolding, they were information processors. And perhaps, he thought, they could support quantum states. Together, Penrose and Hameroff proposed something radical, that consciousness arises from quantum computations inside microtubules. Tiny, delicate states of quantum coherence, like entangled particles, form within these structures, protected from the noisy environment of the brain. And when these quantum states reach a threshold, they collapse. Not randomly, but with purpose. This collapse is what Penrose called objective reduction. A moment where a quantum system chooses a definite state, not through observation, but through the structure of the universe itself. Now imagine billions of these micro-events happening across your brain, orchestrated in time and space. Each collapse, a moment of awareness. Together, they generate what you call consciousness. Not a trick of neurons, but a quantum symphony, echoing at the smallest scales of being. Critics argue this can't be. They say the brain is too warm, too wet, too noisy for quantum coherence to survive. But recent experiments suggest otherwise. In photosynthesis, in bird navigation, in even the sense of smell. Quantum effects have been observed in biological systems. The line between quantum and biological is beginning to blur. And if Orch-OR is correct, then your mind isn't just inside your head. It's embedded in the very fabric of reality. Because objective reduction isn't just about biology. It's a proposal about how the universe works. That the collapse of a quantum wave function isn't due to measurement, but to gravitational differences between possible states. That the universe chooses reality through a kind of self-awareness. If that's true, then consciousness is not an accident. It is a fundamental property of the cosmos, a whisper of the universe looking inward. And suddenly, your thoughts aren't isolated. They're entangled with the structure of space itself. This theory is bold. It hasn't been proven. It might never be. But even if it's wrong, it opens a door to something astonishing. That consciousness might not be generated, but revealed, like tuning a radio to a frequency that was already there. Microtubules then become not computers, but antennas, and you, a receiver of something deeper, a self, unfolding. There's poetry in this model, because if your consciousness is quantum, then your dreams are echoes of universal computation. And your memories are ripples in space-time. Each decision collapses a field of possibilities. Each breath is a quantum beat. And sleep? Sleep becomes a kind of return, a reconnection with that infinite field, before waking brings you back into the narrowed, collapsed world of form. You are not just a brain. You are not just a body. You are a question the universe asks itself, again and again. And maybe that's why consciousness feels so strange, so private, so luminous. Because it's the one thing we can't fully describe, but can't live without. And now, as your thoughts begin to slow, as your brain hums softly in the dark, let that idea settle, that you are not thinking, you are being. And being is not mechanical. It is not neural. It is not digital. Being is quantum. And as you rest in that thought, let's drift to the next theory. One that says there may be many versions of you, each living out a different path. Because next, we'll explore the many worlds interpretation, where every decision branches reality. And somewhere, another version of you is still wide awake. Right now, you're listening to this. But somewhere else, Another version of you pressed pause, and in another world entirely, you never clicked this video at all. This isn't imagination, this is quantum physics. And the theory is called the many worlds interpretation. It begins with a simple problem. In quantum mechanics, particles don't behave like solid things. They exist in many possible states at once. A phenomenon called superposition. A single electron isn't here or there. It's both, until you measure it. Then, and only then, does it seem to collapse into one definite state. This collapse has puzzled scientists for nearly a century. What causes it? Why does the wave of possibilities suddenly narrow into a single reality? For decades, the standard view was that observation caused collapse, that the act of measuring somehow reduced the universe's uncertainty. But in 1957, a young physicist named Hugh Everett had a different idea. What if the wave function never collapsed? What if instead the universe split? Every time a quantum event happens, every time a particle has multiple options, the universe branches. Each possibility is realized. Each outcome becomes its own world. So when an electron chooses path A, another version of the universe exists where it chose path B. And when you choose tea instead of coffee, a version of you chose differently, and that version still exists forever. This is the many worlds interpretation. A vast, eternal, branching tree of reality, where every decision, every quantum flutter, creates a new branch in the infinite forest of existence. It's a radical idea, but here's the twist. It solves many problems in quantum physics beautifully. There's no need for mysterious collapses, no need for external observers. The math works, the equations flow without contradiction. And yet, the implications are staggering, because it means that the universe isn't a single thread. It's a woven tapestry of countless timelines, each equally real, each equally complete. You, right now, are just one version of an infinite self. Somewhere, another you turned left instead of right, said yes instead of no, lived instead of died, and all of it is real. But you can never reach those other worlds. They split away cleanly, like bubbles drifting apart on a river, forever inaccessible. So what does this mean for your choices? If every possible outcome occurs, does choice even matter? Are you just riding a single rail in a pre-written branching script? Maybe not, because while all possibilities happen, you only experience one. And that subjective thread, your lived path, is still yours. It's still sacred. You still suffer its pain. You still feel its joy. Many worlds doesn't erase meaning. It just expands the stage. Your life becomes one voice in a quantum chorus, a melody with infinite harmonies. And some physicists go even further. They say the multiverse isn't just a weird byproduct, it's necessary. To explain quantum behavior, to preserve unitarity in physics, the many worlds interpretation might not just be possible, it might be true. Experiments haven't disproved it, but neither have they proved it. It remains a possibility among possibilities, a theory about a reality you can never see, but might live inside. There's a strange comfort in this, because if you've ever regretted something, ever wished you could go back, know this: somewhere you did. Somewhere you took the risk, made the leap, held their hand, said what needed to be said. And that version of you is living that life. Even as you live this one, it doesn't mean your life is less real. It means reality is bigger than you imagined. And maybe that's the lesson. That existence is not about perfection. It's about perspective. That every path matters because every path is walked. You are not lost in the branches. You are the branch. And as you drift into sleep, Let that idea hold you gently, that every night you dream, you might be glimpsing a parallel life, one breath away, one choice away, one quantum step from here. And now, as this version of you settles deeper into rest, let's continue down the strange river of science, because next we'll journey into a theory where the entire universe is just one bubble in a foaming sea of eternal inflation. It all began with a bang, or so we thought. The Big Bang has long been the standard story of our origin, a single, explosive birth that expanded into galaxies, stars, planets, and life. But what if that's only part of the story? What if our Big Bang wasn't the beginning of everything, but just the beginning of this, a single bubble in a vast, cosmic foam? This is the theory of eternal inflation, a staggering idea that expands our universe into a much bigger multiverse. And it begins with a strange twist on the Big Bang itself. In the early 1980s, physicist Alan Guth introduced the idea of cosmic inflation, that the universe didn't just expand after the Big Bang, it exploded outward at incomprehensible speed, doubling in size over and over again in a fraction of a second. This inflationary burst explains a lot. Why the universe looks so smooth, why distant regions seem strangely connected, why we see the patterns in the cosmic microwave background that we do. But inflation theory had a strange side effect. In some models, inflation never completely ends. Instead, it slows down in certain regions, creating bubble universes where expansion stabilizes and forms stars, matter, and life. But in other regions, inflation continues endlessly, creating more bubbles, and more and more. This is eternal inflation, a universe that is constantly spawning other universes, each with its own laws, constants, and configurations. And our universe? Just one bubble among many, maybe an average one, maybe an odd one, but not the only one. This leads to a vision of reality that's hard to grasp. A multiverse, not made of parallel timelines like in quantum theory, but of entirely separate realms, causally disconnected, forever unreachable, yet just as real. Imagine a vast ocean of inflating space. Within it, bubbles form, each becoming a universe. Some might collapse. Some might stretch on for trillions of years. Some might never form stars. Some might give rise to creatures we can't imagine. And maybe, in one of them, something wonders about us. In eternal inflation, everything that can happen does happen somewhere. Not because of choice, but because of pure physics. Quantum fluctuations in the inflating field create ripples, tiny imperfections that cause one patch to settle, while another keeps stretching. It's like boiling water, where bubbles form at random, but always follow the rules. And just like that, reality becomes a cosmic foam. It's important to understand, we're not talking about galaxies or planets here. Each bubble is an entire universe, with its own space, its own time, its own beginning, and no way for light or information to pass between the bubbles. We are forever sealed inside our own. This might sound like speculation, but it isn't just theory. It's a consequence of our best models. Eternal inflation arises naturally from quantum field theory, from the shape of the inflationary potential, from the way energy landscapes work in the vacuum of space. In other words, we didn't invent this idea to be poetic. It fell out of the math, and it raises deep questions. If there are countless other universes, why do we find ourselves in this one? Why are the physical constants, gravity, electromagnetism, the strength of atoms, so perfectly tuned to allow life? In a single universe, that seems improbable. But in a multiverse, it becomes inevitable. Because if every possible version of physics plays out somewhere, then of course we find ourselves in a universe that supports consciousness. That's the one place where observers can exist. This is called the anthropic principle, not because the universe was made for us, but because we could only appear in the kind of universe that allows us to appear. It's humbling and haunting, because it suggests we are not special, not central, not necessary, just a bubble in a bath. But there's beauty in that too, because it means creation never ends. Reality is not a single explosion, but a blooming fractal, an eternal unfolding of possibility. And somewhere, right now, new universes are being born. Some will be empty. Some will burst into light. Some might cradle minds that wonder about their own beginnings. And maybe, in some distant reality, another voice is whispering this same thought to another sleeper. It's easy to feel small in the face of this idea, to imagine yourself as a speck floating in a bubble, adrift in an ocean of unknowable others. But there's a quiet power in it too, because in this endless blooming, your moment, this moment, still matters. You are the product of one improbable path, one stable bubble, one set of laws that led to stars, planets, cells, and thought. You are the rare flicker in the foam. And as you close your eyes, know this: the universe is still expanding, still inflating, still creating. The multiverse is not a finished book. It's a story that writes itself again and again on an infinite page. And next, we'll travel from the infinite to the cyclical, because some physicists believe our universe doesn't just expand, it collapses and bounces and begins again. We think of time as a line, a beginning, a middle, an end. The Big Bang was the start, the expansion of the universe, its middle, and one day, perhaps, cold, empty stillness, the end. But what if that's not how it works? What if the universe doesn't move like a line, but breathes like a lung, expanding, contracting, rebounding, forever? This is the Ekpyrotic Universe, a theory where the cosmos lives in cycles. It doesn't begin, it doesn't end, it pulses. The word ekpyrotic comes from ancient Greek philosophy. It means conflagration, a cosmic fire that destroys the old world to make room for the new. But in modern physics, it means something more elegant. It means the universe may collapse and bounce back, over and over again. No final death, no permanent birth. Just an eternal rhythm, a cosmic inhale and exhale. To understand this, let's revisit the standard view. In the Big Bang model, the universe began as a singularity, an infinitely dense, hot point that suddenly expanded. This explosion created space, time, matter, and energy, and for nearly 14 billion years, that expansion has continued. Galaxies drift apart, space stretches, the cosmos cools. Eventually, some say, it will all end in darkness, a heat death, where everything is so far apart and so low in energy that nothing more can happen. But the Ekpyrotic model offers a different story. It suggests that what we call the Big Bang wasn't a true beginning. It was a transition from one cycle to the next. Imagine two gigantic, invisible sheets, called brains, floating in a higher dimensional space. These brains occasionally collide, and when they do, the energy release sparks a new universe, our universe, not from nothing, but from the rebirth of everything. Between these collisions, the universe expands and cools, just like in the standard model, but eventually, instead of drifting into entropy, it contracts. Space pulls inward, galaxies converge, energy condenses, and then another bounce, another Big Bang, another cycle begins. This vision of reality is called cyclic cosmology, and the Ekpyrotic model is one of its boldest forms. It solves several problems in physics, like the flatness problem, why the universe is so geometrically smooth, or the horizon problem, why regions of space too far apart to communicate still look nearly identical. In inflation theory, these issues are solved with a brief, super-fast expansion, but in ekpyrotic theory, they're solved over time, through long, slow cycles that naturally smooth and reset the universe again and again. There's a quiet simplicity to it, a sense of cosmic sustainability, no true beginning to explain, no fine-tuned initial conditions, just cycles, echoing beyond memory. Some versions of this theory even suggest that the universe remembers, that tiny quantum imprints from one cycle influence the next, like scars on a cosmic body, carrying information across eons. And this raises a beautiful question. If the universe has lived and died before, how many times has it done so? Are we in the first cycle, the 100th, the trillionth? Are there ancient fingerprints beneath our laws of physics, patterns laid down in cycles long before this one? And if so, does that make our story smaller or bigger? Because in a cyclic universe, death is never the end. It's a doorway. Collapse is not destruction. It's preparation. Even time itself becomes a spiral, not a straight path, returning, revisiting, reframing itself. And maybe consciousness too follows this rhythm. Maybe awareness isn't confined to one cycle. Maybe it too emerges again and again. New forms, new perspectives, same mysterious light. And so, while the standard view sees a universe that fades away, the ekpyrotic model offers a universe that learns to begin again, like seasons, like tides, like breath. It's not just physics, it's poetry in motion, the idea that the universe collapses not in failure, but in readiness, that the end of one cycle makes space for something new, that no moment is truly lost, everything returns. And now, as you drift between thoughts, imagine this rhythm, the stars fading, the galaxies falling inward, the sky going dark, then light again, the next breath, the next birth, the next world. We are not trapped in time, we are carried by it. And now the current carries us forward once more, into a theory where time itself may not move the way we think. Time always flows forward, or so it seems. The clock ticks, the arrow flies, the past becomes memory, and the future remains unknown. But deep inside the fabric of the universe, at the smallest, quietest scales, time begins to behave strangely, and sometimes it flows backward. This is the world of quantum tunneling and time-reverse dynamics, where particles defy barriers and cause may follow effect. It begins with something called the potential barrier. In classical physics, if a particle doesn't have enough energy to climb a hill, it can't reach the other side. Like a ball at the bottom of a valley, it stays there, unable to rise over the ridge. But in quantum physics, particles are described not as points, but as probability waves. And these waves don't stop at barriers, they leak. So even when a particle shouldn't be able to cross, it sometimes does. Not by climbing the hill, but by appearing on the other side. As if reality briefly allowed the impossible. This is quantum tunneling, a phenomenon observed in nuclear fusion, semiconductors, and even biological processes. It's real, it's measurable, and it's deeply unsettling because it suggests that the universe isn't ruled solely by deterministic laws, but by possibility itself. A particle doesn't need permission, it just might. But tunneling is only the beginning. Some interpretations of quantum mechanics, combined with certain equations in physics, suggest that at microscopic scales, the arrow of time can flip, that particles may move from future to past, or exist in a superposition of both. In these interpretations, a particle's behavior isn't fully determined by its past, but by its future too. It's called retrocausality, the idea that future events might influence the present, not in a way that allows paradoxes or time machines, but subtly, quietly, like a whisper from what's yet to come. Imagine throwing a stone into a pond. Ripples move outward, but in quantum physics, some ripples seem to move inward, toward the moment the stone was thrown. Cause and effect become entangled. This doesn't happen at the level of coffee cups or car rides, but at the level of electrons, photons, and the quantum fields they dance through. Some experiments in quantum optics even hint at this behavior. In certain setups, measurements made in the present appear to influence outcomes that were decided in the past, not by changing history, but by shaping probabilities. It's as if reality holds its breath, waiting for the whole equation, past and future together, before it reveals what happened. This challenges everything we think we know about time. We imagine time as a one-way street, a flowing river that moves only forward. But in physics, the fundamental equations are time symmetric. They don't care which direction time moves. The laws work just as well backward as they do forward. It's only at the scale of human experience, where heat flows, entropy rises, and memories accumulate, that time seems to move in one direction. At the quantum level, time is negotiable, and this opens up strange possibilities. What if your brain's chemistry, influenced by quantum fluctuations, is subtly shaped by both past and future? What if choices aren't just about what came before, but also about what's yet to unfold? You may never feel this, you may never know, but somewhere, in the tiniest corners of your neurons, time might be dancing in both directions. And quantum tunneling, it might be more than just a physical trick. It might be a reminder that the universe is not confined by walls, that boundaries, like time, like space, like cause and effect, are more porous than they seem, that sometimes the shortest path isn't through, but around, and sometimes the universe doesn't wait for permission. It just moves, it slips, it tunnels. There's beauty in this uncertainty, because it means the future is not fixed, the past is not locked, and the present is not alone. You are part of a web that stretches in all directions, through time, through possibility, through being. And now, as your mind sinks deeper, you may feel that looseness, that quiet detachment from sequence. You are no longer just moving forward. You are floating in a space where time folds, where before and after are soft. And maybe, as you sleep, some version of you is tunneling, slipping through a boundary you cannot see, moving not toward the future, but toward something deeper. And now, let's explore the seeds of everything. Because next, we'll enter a moment of trembling nothingness, when the universe was just a flicker. A theory where tiny quantum fluctuations gave birth to galaxies, where the randomness of the smallest scale became the structure of the cosmos. Before the stars, before the galaxies, before even time had a rhythm, there was silence. Not empty, not full, just silence, trembling with possibility. And then, in the briefest blink, everything changed. The universe expanded faster than light, stretched beyond imagination, and in that stretching, something extraordinary happened. Tiny quantum jitters, so small they defy comprehension, became the scaffolding for everything. This is the story of quantum fluctuations and cosmic inflation, how randomness at the smallest scale built the architecture of the entire cosmos. To understand it, We return to a moment just after the Big Bang, not a second later, not even a microsecond, but a fraction of a second, a moment so early that time itself was still learning to tick. This is when inflation occurred, a rapid, exponential expansion of space, so fast and so vast that the observable universe ballooned from subatomic to cosmic in an instant. Inflation smoothed out the wrinkles of the newborn universe, wiping away irregularities, spreading energy evenly across a growing canvas. But not perfectly, because at the quantum level, nothing is perfectly still. There is always noise, always fluctuation, always uncertainty. Even in the vacuum of space, what we call nothing, particles flicker into and out of existence. These fluctuations are governed by the Heisenberg uncertainty principle, the idea that you can't perfectly know a particle's position and momentum at the same time. So the early universe was full of this jittering uncertainty, little bumps, little dips. And as inflation expanded the universe at near infinite speed, it stretched these tiny fluctuations to cosmic scales. What was once smaller than an atom became larger than galaxies. These amplified quantum tremors became regions of slightly higher or lower density. Over billions of years, gravity pulled more matter into the denser regions, and slowly, those tiny ripples became the stars, the planets, the galaxies. Everything you see in the night sky was seeded by quantum randomness, frozen into place by inflation. It's almost unthinkable that the universe's structure, its great walls, clusters, and filaments, traces back to quantum blips in a sea of expanding space, that the reason some regions glow with billions of stars and others remain dark is because of what happened in the first trillionth of a second. This is why the cosmic microwave background, the afterglow of the Big Bang, is not uniform. It has tiny variations in temperature, minute differences in energy, and those differences match the predictions of inflation combined with quantum fluctuations. It's as if the early universe painted itself with a brush too small to see, and yet the pattern remains. Some say this feels like chaos, that the universe is built on randomness, but there is order within it, because quantum fluctuations are not just noise, they are statistical, they follow rules, and those rules created a cosmos with just enough clumping to form stars, but not so much as to collapse, just enough smoothness to allow galaxies, but not so much as to erase them. It's a delicate balance, and somehow the physics of quantum mechanics and the timing of inflation landed on just the right values. Why? We don't know. Perhaps it was chance. Perhaps it was necessity. Or perhaps it's the only kind of universe where questions like this can be asked. Quantum fluctuations are usually confined to atoms, but in those early moments, they touched the stars. And it makes you wonder, what else is shaped by such invisible forces? What thoughts are seeded by fluctuations in our minds? What moments in your life began as imperceptible shifts? A glance, a word, a thought you didn't notice, and now here you are. Like the galaxies, you are an echo of tiny beginnings, a structure built from quiet chaos. And now, as you rest beneath the same stars that once flickered as equations, you carry that silence within you. You are not separate from the cosmos. You are its continuation. Your breath is a ripple, your heartbeat, a rhythm born from quantum dust. And as you fall into sleep, let this thought remain, that from uncertainty, beauty can emerge, that randomness can build worlds, that chaos can whisper meaning. And now, let us drift towards something stranger. What if particles could move faster than light? What if, with the right conditions, information could travel backward in time? You pick up the phone, but before you say anything, you hear a voice, your own voice, from the future. It tells you what's about to happen, And it's right. Then the call ends, and the timeline has changed. This is the strange and paradoxical idea behind the Tachyonic Antitelephone, a hypothetical device that could send information backward through time. It starts with a particle that doesn't exist, but might. It's called a tachyon. In theory, a tachyon is a particle that always travels faster than light, not just hypothetically fast, beyond the universal speed limit. Einstein's theory of relativity tells us that as an object approaches the speed of light, its mass increases and the energy required to accelerate it becomes infinite. This is why nothing with mass can ever reach the speed of light. But what if something starts out already beyond that threshold? A particle that can't slow down to light speed, because it would require infinite energy to stop. That's the tachyon, and its existence would turn time inside out. Because in special relativity, faster than light travel isn't just about speed. It changes the sequence of events. What looks like cause and effect in one frame of reference can become effect and cause in another. A signal sent with a tachyon might arrive before it was sent, and that means, in principle, you could send information to the past. This leads to the idea of a tachyonic antitelephone, a theoretical device using tachyons to communicate backward in time. Imagine two people, far apart, each with such a device. One sends a message using tachyons. Because of how space-time behaves at superluminal speeds, the other receives it before it was sent. Now reverse it. They respond, and the message arrives even earlier than the first. Repeat this loop enough times, and you could receive a message before you even decided to send one. The loop closes. Causality unravels. You could, in theory, prevent your past self from sending the original message, and now you're caught in a paradox. This is the problem of retrocausality. It breaks the very rules that hold logic together, the same kind of paradox as going back in time and preventing your own birth. It sounds absurd, and yet the math, at least on paper, allows it. So why don't we observe these paradoxes in real life? There are many reasons. First, we've never found any evidence that tachyons exist. Despite extensive searches, no particle has ever been observed traveling faster than light. Second, even if tachyons were real, it's unclear how we could control or detect them. They might violate other laws of physics, like conservation of energy or quantum coherence. And finally, the universe seems to protect itself from paradoxes. This idea is called the chronology protection conjecture, proposed by Stephen Hawking. It suggests that the laws of physics conspire to prevent time travel paradoxes from occurring, perhaps through quantum instability, feedback loops, or unknown principles. In other words, nature closes the loop before the loop can break reality. Still, the tachyonic antitelephone remains a fascinating thought experiment, because it asks a deeper question. What is time? Is it a flow, a direction, a consequence of entropy, or is it just the way we perceive the structure of space-time? In some interpretations of quantum mechanics and relativity, time is not fundamental. It's emergent, and if time can be bent, stretched, or reversed at the quantum level, then maybe, just maybe, causality itself is flexible, not broken, but more mysterious than we ever imagined. And it makes you think, what would you say if you could speak to your past self? Would you offer a warning, a comfort, a question? Would it change anything? Or was the message always going to arrive? Because it already had. In these quiet, abstract corners of physics, the line between what is and what was begins to dissolve. And maybe that's the lesson. That time is not a hallway, but a tapestry, woven in both directions, a pattern that holds more than just memory, but possibility. And now, as you lie still in the present, Know that the past and future are not as far apart as they seem. They may be touching you right now, in dreams, in déjà vu, in the deep architecture of your mind. You are not just moving through time, you are part of how time moves. And now, let's return to a classic paradox, where a single cat is both alive and dead until you dare to look. There's a box. Inside it, a cat. You don't know if it's alive or dead. And until you look, physics says it's both, alive and dead, at the same time. Not metaphorically, literally. This is the famous thought experiment known as Schrödinger's cat, a paradox at the heart of quantum mechanics. And it's not just about a cat. It's about reality itself and whether it exists when we're not looking. Let's begin with the strange world of superposition. In quantum mechanics, particles don't have fixed positions or states. Instead, they exist in a blend of all possible states at once. An electron can spin up and down at the same time. A photon can go through both slits of a screen simultaneously. A particle can be in multiple places at once, until it is observed. When you measure it, the wave of possibilities collapses into a single outcome. Before observation, there is probability. After observation, there is reality. Now, enter Owen Schrödinger. In 1935, to illustrate the absurdity of applying quantum principles to everyday objects, he imagined this scenario. Place a cat in a sealed box. Inside the box is a tiny bit of radioactive material. There's a 50% chance it will decay within an hour. If it does, a Geiger counter detects it and triggers a mechanism that shatters a vial of poison. The cat dies. If the atom does not decay, the poison isn't released and the cat lives. Simple enough. But here's the twist. According to quantum theory, the atom is in a superposition, both decayed and not decayed, which means the mechanism is also in superposition, both triggered and not triggered, and the cat also in superposition, alive and dead, until you open the box. Only then does the system collapse into one reality. This sounds ridiculous, and that's the point. Schrödinger's cat was never meant to be a real experiment. It was a critique, a way to expose the strange implications of quantum theory. But here's the uncomfortable truth. The math agrees with the cat. In quantum physics, everything, not just particles, but systems, machines, even you, can exist in superpositions. You don't notice this because superposition is delicate. It breaks down quickly in large warm systems. But at the fundamental level, it's real. And this raises a haunting question. If reality doesn't choose until we observe it, what happens when no one is looking? Does the moon exist when no one sees it? Is the universe real when unmeasured? Or is observation, conscious or unconscious, part of how reality comes into being? Some interpretations say yes, that the act of measurement isn't just revealing truth, but participating in it. That the universe is a kind of potential, collapsing into form only when interacted with. Others say no, that the collapse is just a mathematical artifact, a trick of language and scale, that the universe is what it is, regardless of your attention. Still others, like the many worlds interpretation, say the cat never really chooses. Instead, both outcomes happen. In one world, the cat lives. In another, it dies. And you split with it. But here's what matters. At the edge of quantum thought, reality becomes ambiguous, not fixed, not absolute, but conditional. And if that's true, then maybe certainty is a luxury of scale. At the quantum level, the world is undecided, and you are part of the decision. You are not a spectator in this universe. You are a participant. Each moment you look, listen, act, you help collapse the possibilities into reality. You turn the maybe into the is. The cat becomes real when you care to look, and so does everything else. This doesn't mean the universe depends on you to exist, but it may depend on interaction, on entanglement, on participation. Reality is not static, it's relational, and you, quiet, breathing, thinking, are entangled with it. So as you lie here, between wakefulness and sleep, know that you are not separate from the mysteries of physics. You are a piece of the puzzle, an observer, a co-creator. Somewhere in a metaphorical box, a cat still waits. Not because it's real, but because reality is still unfolding. And now, let us move from paradox to principle, because next, we'll explore a strange mathematical truth, that you can't comb the hair on a sphere without creating a whirl. A theorem with deep implications for physics, fluid flow, and the unseen patterns of the cosmos. Now try to comb all the hairs flat, so that none stick up and none swirl around. No matter how carefully you comb, no matter where you start, there will always be at least one stubborn spot. One place where the hair swirls, sticks up, or refuses to lie flat. This isn't just a grooming problem, it's mathematics, and it's called the hairy ball theorem. A strange, delightful idea from the field of topology, a branch of mathematics that studies the shapes and surfaces of space. And while it may sound silly, this little theorem reveals deep truths about how nature works. The hairy ball theorem says this: there is no non-vanishing continuous tangent vector field on even-dimensional n-spheres. In plain language, you can't smoothly comb the hairs on a sphere without creating a cowlick. Or to put it more mathematically, any attempt to assign a direction at every point on a sphere, without any discontinuities or zeros, will fail. There will always be at least one point where the direction breaks down. This might seem abstract, but this simple topological insight has surprising consequences. Take the Earth, for example. Imagine the wind at every point on Earth's surface. If you tried to represent the wind as tiny arrows pointing in the direction the air is moving at each location, the hairy ball theorem tells us something profound. There will always be at least one point where the wind is calm, a place with no direction at all, a zero, a stillness, a swirling vortex, or the eye of a storm. This isn't a coincidence, it's a mathematical necessity, and we see it in nature. Hurricanes, whirlpools, tornadoes. These aren't just weather events, they're expressions of topology, the unavoidable consequence of trying to comb the atmosphere on a sphere. The same idea applies in fluid dynamics, magnetism, and even in theoretical physics. Anywhere you try to map a smooth, continuous vector field on a sphere, you will encounter singularities, points where the system must break down. And this leads to a deeper reflection. Sometimes disorder is not failure, it's a requirement. Sometimes the universe needs turbulence, not as a flaw, but as a feature. Because even in a system striving for perfect smoothness, there must be moments of chaos, swirls, eddies, irregularities. Nature uses them not as mistakes but as anchors. Stability within instability. You can try to make everything neat, everything aligned, everything under control. But the hairy ball theorem reminds us there will always be one place where things won't fit. And that's okay, because from that point of breakdown, new structures can form, new flows can emerge, new systems can adapt. There is beauty in this inevitability because it means complexity is built into the geometry of space itself. And if the Earth cannot be combed smooth, if the very air we breathe must twist and spin, then perhaps our thoughts too must sometimes swirl. Perhaps peace doesn't come from perfect stillness, but from learning to live among the whirls. The hairy ball theorem also touches on something deeper. That topology matters, that the shape of things determines what's possible, not just their mass or motion or composition, but their shape. And shape in mathematics can be more powerful than force. It tells us what kinds of fields can exist, what symmetries must break, what patterns must form. This is why physicists care about topology, because sometimes a simple theorem about hair on a ball tells you why storms form, why magnetic fields behave the way they do, or why certain particles can or cannot exist. In this way, the hairy ball theorem becomes more than a curiosity. It becomes a lens, a way to see the rules behind the rules, the geometry behind the chaos. And now, as you rest, think about your own inner landscape. Have you tried to smooth out every thought, to line up every feeling, to make everything tidy, continuous, under control? It's okay if you couldn't. It's okay if there's a swirl, a spot that sticks up, a thought that won't settle. That's not a flaw. That's the nature of spheres. That's the truth of wholeness. And now, let's keep exploring the quiet elegance of thermodynamics, because next, we'll look at how ice cream melts, how crystals dissolve, and how the small always feeds the large. Picture a bowl of ice cream. Left untouched, it begins to melt, but before it turns to liquid, something quieter happens. Look closer. At the texture, you'll notice that the smaller ice crystals begin to disappear, while the larger ones slowly grow. It's subtle, unseen by the eye, but the pattern is precise. This process has a name: Ostwald Ripening. It's a thermodynamic phenomenon that describes how, over time, small particles shrink and large ones get larger, not through melting, but through molecular migration. And though it begins in ice cream, it ends in stars, in rocks, in clouds, in the fabric of material change. The principle is simple. In a mixture of solids, like crystals in a liquid, smaller particles dissolve more easily. They have higher surface energy. They are less stable, so their molecules tend to break away and float through the surrounding medium, eventually reattaching to larger, more stable crystals. Little by little, the big grow bigger and the small vanish. It's a kind of silent sorting, not by force, but by preference, built into the physics of surfaces. Ostwald Ripening is named after Wilhelm Ostwald, a Nobel Prize-winning chemist who first described the process in the early 20th century. Since then, we've seen it in action everywhere. In metallurgy, where grains of metal grow and shift over time. In emulsions, like milk or mayonnaise, where droplets coalesce and restructure. In geology, where minerals slowly crystallize deep within the earth. Even in the human body, in bones, teeth, and biological tissues, this process can play a role. Wherever matter is suspended in another phase, solid in liquid, liquid in gas, Ostwald Ripening is at work, and it always moves in the same direction, toward equilibrium, toward a state where energy is minimized, where the system becomes more stable, more coarse, more mature. It's not about destruction, it's about refinement, and it reflects something deeper in nature, that not all change is violent, not all growth is explosive. Sometimes it is slow, quiet, invisibly patient, and yet it transforms everything. Ostwald Ripening is governed by chemical potential, a measure of how likely particles are to move from one place to another. Smaller particles, with their higher curvature, have a higher potential. They are eager to dissolve. Larger particles, with lower curvature, have lower potential. They are more likely to receive. And so a gradient forms. Matter flows from the small to the large, from the temporary to the enduring. It's a story of thermodynamic migration, and it mirrors so much of what we observe in life, where the loud often fades and the quiet endures, where the flashy peaks early, but the patient builds slowly and lasts. You can think of it as a law of consolidation, a physics of refinement, and maybe even a metaphor for memory, because in your mind too, not every thought remains. Some dissolve, some fade, some flow into larger, deeper patterns, the ones you carry for life. The things that grow in you are not always the newest or most obvious. They are the ones that persist, that draw meaning slowly from the rest. Ostwald Ripening tells us something comforting, that even in decay, there is design, that even as small pieces disappear, they are not lost. They become part of something larger. And this applies to more than just matter. It applies to systems, to relationships, to knowledge, to experience. In time, what's unstable fades, what's fragile dissolves, and what remains is stronger. Not because it won, but because it integrated, because it absorbed, balanced, endured. And so, the next time you see crystals forming, or clouds thickening, or even your ice cream changing texture, know that something profound is happening. Molecules are moving, energy is balancing, equilibrium is calling, and the system listens, even silently, even slowly. And now, as your thoughts settle like particles in a calm fluid, remember, not all progress is fast, not all growth is visible, but even the stillest systems are shifting, refining, ripening, and from this quiet process, order emerges. And next, we move back in time to a universe of fire and light. Because before stars, before matter, the cosmos was a sea of glowing plasma. And understanding this primordial soup helps us unlock the secrets of the cosmic microwave background. Before atoms, before stars, before the fabric of matter cooled into the shapes we know, the universe was light and fire, a glowing fog, a seething ocean of plasma, no solid, no liquid, no gas, just pure energy, too hot for structure. And yet, from that chaos, everything emerged. This is the story of the plasma-filled cosmos, the universe in its earliest phase, a time when light could not move freely, when particles and photons were trapped in a cosmic dance. And understanding this moment reveals one of the most profound discoveries in science, the cosmic microwave background. Let's begin at the beginning. The Big Bang was not an explosion in space, it was an expansion of space. Hot, dense, and uniform. In the first few moments, energy condensed into particles, quarks, electrons, neutrinos. Then, as things cooled, quarks bonded into protons and neutrons. But it was still too hot for atoms to form. Every time a proton tried to catch an electron, a stray photon would knock them apart. The universe was ionized, meaning charged particles roamed freely. This is plasma, a state of matter where nuclei and electrons float separately, interacting constantly with light. In this plasma-filled universe, photons, the particles of light, couldn't travel far. They were constantly scattered, absorbed, redirected. It was like trying to see through fog. No light could move in a straight line. The universe was opaque. But over time, things cooled. Around 380,000 years after the Big Bang, the temperature dropped low enough for electrons and protons to finally combine, forming the first hydrogen atoms. This process is called recombination, and with neutral atoms came transparency. Suddenly, photons were free. They streamed outward in all directions, no longer blocked, no longer trapped. And that ancient light, is still moving today. It has stretched, cooled, and faded with the expansion of space. But it hasn't disappeared. We see it now as a faint, uniform glow that surrounds us from every direction. It's called the Cosmic Microwave Background, or CMB, and it is a snapshot of the moment the universe became transparent, a fossil of light, a baby picture of the cosmos. Discovered in 1965 by Arno Penzias and Robert Wilson, this background radiation was one of the greatest confirmations of the Big Bang Theory. But more than that, it tells a deeper story. Because this light isn't perfectly uniform, it has tiny fluctuations, slight differences in temperature and energy, like ripples frozen in time. And those fluctuations match the predictions of quantum mechanics, inflation, and gravitational evolution. They are the seeds of structure, the fingerprints of the earliest whispers. Galaxies, clusters, voids. They all trace their lineage back to this glowing map. It is poetry, encoded in photons. And it all began in the plasma. You can think of plasma as the primordial voice of the universe. Chaotic, but not random. Shifting, but not lost. Its behavior follows the rules of electromagnetism, governed by Maxwell's equations. Complex and beautiful. In plasma, waves form, fields interact, particles spiral around invisible lines of force. Even today, we study plasma in stars, in solar flares, in neon lights, and fusion reactors. But in the early universe, plasma was everything. And when it cleared, it left behind a perfect moment, a light that has travelled for over 13 billion years to arrive, here, now, faint, but eternal. The CMB is not just background noise. It is evidence that the universe had a beginning, that it was once hot, dense, and glowing. It is the light that once touched everything and never stopped moving. And now, it touches you. You are bathing in ancient light. Every second, photons from the dawn of time pass through your body. They are harmless, gentle, ghost-like, but they carry a message that you are part of a universe with a past, with memory, with pattern. You are not adrift in chaos. You are held within history. The plasma has cleared. The light has come through. And what it reveals is wonder. And now, as you settle deeper into stillness, let your thoughts soften. Let them become like that early universe, warm, glowing, unstructured. Because next, we'll drift into a theory even stranger, where our universe might be a floating sheet in a higher dimension, where reality could collide with another, resetting everything. We think of the universe as everything: galaxies, stars, nebulas, dark matter, time and space. But what if all of it, everything we know, is just one surface, floating in a higher dimensional reality, like a bubble drifting through a vast, unseen ocean? This is the idea behind Braneworld cosmology, a radical theory born from string theory and extra dimensions. And at the center of this idea is something called the Big Splat. Let's begin by reimagining space. In string theory, the fundamental building blocks of reality are not point particles, but tiny, vibrating strings. These strings don't just vibrate in 3 dimensions. They require more. 10, maybe 11. Some compact, some extended. And within these higher dimensional frameworks exist structures called brains, short for membranes. Brains can have many dimensions. Some may be point-like, others could stretch across vast distances. And according to certain models, our entire universe is a 3-brain, a three-dimensional surface embedded within a higher dimensional bulk. Imagine a sheet of paper floating in the air. That sheet is our universe. The air around it is the bulk, a higher dimensional space we cannot perceive. Everything we know, particles, light, gravity, is confined to our brain, except for gravity itself. In these models, gravity is different. It can leak. It can move through the bulk. This might explain why gravity is so weak compared to other forces. It's not missing. It's spreading, bleeding into higher dimensions we cannot touch. But here's where things get stranger. In the Braneworld model, developed by Lisa Randall and Raman Sundaram, and in others inspired by M-theory, it's possible that other brains exist. Parallel universes floating nearby, in dimensions we can't detect. And just like waves on water, these brains can ripple, they can move, and sometimes they can collide. When two brains crash into one another, the energy of the collision could create a burst of heat and matter, a new Big Bang. This is the Big Splat, a cosmic collision, not from nothing, but from geometry, from movement. Our universe, our Big Bang, may have been born from such an impact, and it may not be the first. Because brains can move in cycles. They approach, they collide, they rebound. A rhythmic smashing and reforming of entire universes. Each splat birthing a new cosmos, each one with its own timeline, its own expansion, its own fate. In this view, the Big Bang wasn't the beginning of space and time, but a moment of transition, a ripple in a higher dimensional ballet. It's difficult to imagine. We're so used to thinking in 3 dimensions with time as a straight arrow. But in these models, reality is a fabric we don't fully see, and we're only a surface wrinkle. This theory also provides new ways to think about old problems, like why the universe is so flat, or why gravity behaves the way it does. If gravity can move into the bulk, if other brains are nearby, if space is layered like sheets of paper pressed together, then perhaps the rules we know are only part of the story. And it begs a haunting question. What if another brain is approaching? What if, right now, beneath the silence of night, a slow drift is unfolding in higher dimensions? What happens if we collide again? Would it be the end? A reset? A rebirth? Would we know? Maybe not. Maybe the splat is instant, recreating reality so quickly that we don't even feel the transition. Maybe time itself restarts. A new arrow, a new history, a new beginning. Or maybe some whisper of memory persists, some quantum trace of what came before. In this view, our universe is not central, not unique. It is one surface in an invisible sea of shifting possibility. And you, a small point on this brain, are drifting with it, through dimensions you cannot see, through spaces that do not touch light, through rhythms that unfold beyond time. It's humbling, strange, beautiful, because it means we are not alone in the void. We are part of a larger structure, one that might be creating, destroying, and renewing universes all the time. And we are just one ripple. So as you rest, know that your world, your stars, your gravity, your breath, are all suspended on something deeper, something silent, something vast. And next, we'll return to the mystery of mind, because some believe consciousness itself may be quantum, but others push back. Next, we'll explore the fierce debate. Does quantum mechanics really shape consciousness, or is it just wishful thinking? The brain is complex, the mind mysterious, and consciousness, that vivid, private experience of being, remains one of the greatest unsolved puzzles in science. Some have turned to quantum mechanics for answers, suggesting that thought, awareness, maybe even the soul, emerges from subatomic processes beyond classical explanation. It sounds profound and poetic, but not everyone agrees. Many scientists push back, arguing that quantum consciousness is less a theory and more a myth. Tonight, we drift into that tension between wonder and evidence, between curiosity and critique. Let's begin with the idea itself. Quantum consciousness theories propose that the brain, or parts of it, operate in a quantum state, that thoughts arise from particles entangled, from wave functions collapsing, from coherence hidden inside neurons. One popular model, orchestrated objective reduction, or Orch-OR, suggests that microtubules in brain cells support quantum computations, that these computations collapse in structured ways, giving rise to consciousness. It's elegant, and it ties mind to the fabric of physics itself. But the critiques are sharp. The first is environmental. The brain is warm, wet, and noisy. Quantum coherence, the delicate state where particles exist in multiple possibilities at once, is extremely sensitive. It breaks down easily in warm systems. That's why quantum computers need to be cooled near absolute zero to protect their quantum states. Critics ask, how could fragile quantum processes survive in the messy, chaotic conditions of the human brain? Supporters of quantum mind theories reply that biological systems have found ways to maintain coherence, citing examples from photosynthesis, bird navigation, and olfaction. But these effects occur over short timescales, in highly specialized conditions. Nothing yet proves that coherent quantum states can persist long enough or at the right scales to create thought. Another critique is about necessity. Is quantum physics even needed to explain consciousness? Many neuroscientists believe that the complexity of classical systems, the interactions of billions of neurons, neurotransmitters, and feedback loops, is enough. The brain is already astonishing without invoking quantum mechanics. Why add mystery where we already have challenge? Quantum mind theories may be beautiful, but beauty is not proof. They risk falling into what some call quantum mysticism, using the strangeness of physics to explain the strangeness of consciousness without clear mechanisms. It becomes tempting to say, I don't understand how thought works, and I don't understand quantum mechanics, so maybe they're the same. But science demands more than similarity. It demands structure, prediction, evidence. So far, quantum mind models remain speculative, elegant, yes, but unproven. Still, the critics don't dismiss the mystery. They acknowledge that consciousness remains a profound challenge, and quantum mechanics does play a role in neural activity at the level of ion channels, molecular reactions, and fundamental energy exchanges. The question isn't whether quantum physics is present, it's whether it's essential. Is consciousness a quantum effect, or just a phenomenon that includes quantum components as all physical systems do? There's a third position, one that doesn't reject quantum mind theories, but places them in context. It says, we don't yet know what consciousness is, so let's keep exploring. Let's not rule out quantum theories too quickly, but let's also not overreach. Let's study, let's model, let's measure. Because the truth may not lie in physics or neuroscience alone, but in the space between, where information, biology, and uncertainty intersect. After all, consciousness may not be one thing. It may be emergent, layered, contextual. Maybe it's not caused by quantum events, but shaped by them. Maybe the mind is like a coastline, formed by waves, but not made of water. In this way, quantum mechanics could still play a role, not by computing thought, but by setting the probabilities within which thought unfolds. And that idea, while more modest, may still be revolutionary. It brings humility to the conversation. Because for all our models, all our debates, the inner glow of experience remains uncaptured, unmeasured, unreduced. You are aware, you are listening, feeling, reflecting, and no equation, not yet, can describe that. So whether consciousness is quantum or classical, mechanical or mysterious, it remains precious. A frontier not only of science, but of self. And now, as your own consciousness begins to drift toward dreams, we move into a theory of bold defiance. A universe that does not begin, does not explode, but simply always is. We're told the universe had a beginning, a moment of birth, a singular explosion, the Big Bang, and since then, expansion, evolution, a long unfolding of time. But for a while, another vision stood beside that one, a theory of quiet persistence, of infinite duration, of no beginning at all. This was the steady-state universe, not an explosion, but a flow, a cosmos that simply always was, and always will be. It begins with a question of philosophy. Why should the universe have a start? Beginnings imply causes, causes demand explanations. But if the universe never began, perhaps it never needs to be explained. This was the appeal of steady-state cosmology, a theory developed in the late 1940s by Hermann Bondi, Thomas Gold, and Fred Hoyle. According to the steady-state model, the universe is eternal and unchanging on large scales. Yes, it expands, but as it does, new matter is continuously created to keep the overall density of the universe the same. Galaxies recede, but new ones form. Voids appear, but they're gently filled. The universe flows, but never changes. It's like a river, always moving, yet always there. This idea elegantly avoided the need for a Big Bang. No singularity, no early fireball. Just a constant, balanced creation. But then, the evidence arrived. In 1965, Arno Penzias and Robert Wilson discovered the cosmic microwave background. A faint glow of radiation coming from all directions. A fossil, a memory, a remnant of a time when the universe was hot, dense, and glowing. Exactly what the Big Bang predicted, but not what the steady-state model allowed. And just like that, the theory began to fade. Most cosmologists embraced the expanding universe model. The Big Bang became the standard, and the steady-state universe became a chapter in history. But still, there's something beautiful about it. The idea of a cosmos without beginning, without end, without drama, just a quiet, eternal equilibrium. Some modern theories even echo this ancient calm. In cyclic cosmologies, the universe repeats itself forever. In conformal models, the end of one universe becomes the seed of the next, a new kind of steady state. And in some interpretations of quantum gravity, space and time may emerge from deeper timeless structures. So maybe the steady state idea isn't dead. Maybe it's transformed. Maybe we're finding new ways to ask the same old question: what came before the beginning? Maybe there was no before, no after, just is. An existence that doesn't need a reason, a cosmos that is its own cause. It's a humbling thought, because it means we may never find the moment it all started, because maybe it didn't. Maybe the universe is not a story with a first page, but a poem without origin, and you, a line in that poem, written in the syntax of stars. Tonight, as you rest, let this be enough, that the universe is here, and so are you. And maybe that's all there ever was. Stillness, being, forever unfolding. Close your eyes and imagine this. You are floating in space. No stars, no planets, just darkness. Suddenly, a brain appears, fully formed, self-aware, complete with memories, emotions, even the illusion of a life once lived. This brain has no body, no history, and yet it believes in both. It thinks it was born. It thinks it has a name. It thinks it's you, but it isn't. This is the paradox of the Boltzmann brain, one of the strangest implications of thermodynamics and modern cosmology. It begins with the second law of thermodynamics. Entropy tends to increase. Systems move from order to disorder. Ice melts. Stars burn out. Everything decays. But in physics, given infinite time, even highly improbable things become possible. Very rarely, particles might spontaneously arrange themselves into more ordered states, like a gust of wind forming a sandcastle by accident. Unlikely, but not impossible. Now apply that logic to the universe. Over vast stretches of time, in an endlessly expanding cosmos filled with quantum fluctuations, the most unlikely configurations could randomly appear, including a brain, a fully formed conscious mind, assembled not by biology, but by statistical accident, no evolution, no universe, just enough matter, energy, and structure to create one brief flicker of thought, and then silence. No one sees it happen, no one confirms it. But for a moment, this brain thinks, remembers, feels. It may believe it had a childhood, a family, a world. But all of that is illusion, a side effect of its random construction. It never lived. It was never born. It just briefly existed. And here's the twist. Some physicists argue that if the universe is infinite and old enough, then Boltzmann brains are not only possible, they could outnumber real observers like you and me, because it's far more probable for a single brain to fluctuate into existence than for an entire universe like ours to emerge and evolve naturally. This leads to a terrifying implication. If you accept this reasoning, then you might be a Boltzmann brain, a momentary illusion floating in chaos, with memories of a world that never existed. Of course, most scientists reject this conclusion. It feels wrong. It violates common sense. And in physics, theories that lead to absurd predictions, like Boltzmann brains being the dominant form of consciousness, are considered suspect. So cosmologists have looked for ways to disprove this outcome, to show that realistic models of the universe don't favor these random minds. But the problem isn't fully solved. The paradox remains. If the universe is infinite and eternal, what kinds of observers should we expect to be? The ones born from stars, atoms, and evolution, or the ones that just happen? It's a question not just about physics, but about identity. What makes you real? Your memories, your body, your history. If all of those could be faked by a cosmic accident, then what separates a person from a pattern? And how do you know you weren't assembled just moments ago? You don't, not completely. But here you are, listening, breathing, feeling the weight of existence. Maybe that's all the reality you need. Maybe what matters is not how you came to be, but what you do with the time you have. And now, as you drift deeper into this strange idea, let it soften, let it fade into the dark. Because next, we'll explore how reality itself might emerge from quantum competition, where survival of the fittest isn't about biology, but about which version of reality gets to exist. What if reality is just what survived, not what is? But what outlasted all the other possibilities? What if, deep in the quantum world, our classical universe wasn't chosen, but selected? This is the strange, elegant idea behind quantum Darwinism, a theory that blends the randomness of quantum physics with the ruthless logic of evolution. And it might explain why you see a world of solid objects definite outcomes and familiar cause and effect, instead of a shimmering mess of overlapping probabilities. Let's begin with a problem. In quantum mechanics, everything exists in a superposition. Particles aren't here or there, they're both. A cat isn't alive or dead, it's both until you look. But in the world we live in, you never see superpositions. You never see a table that's both present and not, or a car that's driving and parked at once. So where do all the other possibilities go? Why does the quantum weirdness vanish when things get big? Why does the world seem classical? This is called the measurement problem in quantum physics. And for decades, scientists answered it with a concept called decoherence. Decoherence says that as quantum systems interact with their environment, they lose their fragile superposition. Their uncertainty leaks into the surroundings, spreading across atoms, photons, molecules, until the quantum state collapses into something definite. But decoherence alone doesn't explain why we always see the same reality, why observers all agree. That's where quantum Darwinism steps in. It proposes that just like genes in evolution, certain quantum states are more likely to survive. They're more stable, more easily more likely to spread their information, and those are the states we see. The idea was developed by physicist Wojciech Zurek in the early 2000s. He proposed that when a quantum system interacts with its environment, say a particle bouncing light off an object, the environment doesn't just erase superposition, it records it, makes copies of it, spreads it far and wide. But only certain states are easy to copy. Only certain states get duplicated again and again, like a successful gene. These states are called pointer states. They are robust, resistant to interference, and able to imprint themselves on the world. So while a quantum system could contain many possibilities, only the fittest states, the most copyable ones, become visible. They outcompete the rest. The universe, in this view, is constantly performing a kind of selection, not natural selection, but quantum selection. Reality, as you know it, is the result of a vast competition among quantum possibilities, where only the stable survive. What you experience as real isn't the only thing that could have happened. It's the thing that could be copied the most, the outcome that got etched into enough atoms, enough photons, enough of the environment, that it became unavoidable. In this way, quantum Darwinism explains why reality feels so solid. Not because the quantum world isn't real, but because only certain parts of it ever make it to the surface. You could think of it like ripples in a pond. Every action sends out waves, but only the clearest, most coherent ripples travel far enough to be seen. Everything else fades. This also explains why multiple observers see the same world. They're not collapsing the wave function in different ways. They're all reading from the same copies, the same records scattered across the environment. Reality is not created by each observation. It's revealed through shared information. This also means that objectivity, the idea that the world exists independently of your mind, isn't built in. It's emergent. It forms when quantum states are redundantly recorded in ways that many observers can agree on. In other words, reality becomes real when it becomes public, when it's copied again and again into the fabric of the world. And yet, this doesn't remove the mystery. It only reframes it. Because underneath all of this structure is still a quantum sea of unrealized possibilities. The other outcomes, the other branches, the fragile patterns that lost the race. You don't see them, but they were there. They just didn't survive. Quantum Darwinism gives us a quiet answer to the question of why the world looks the way it does. Not because it's the only way it could look, but because it's the only way that lasted. It reminds us that what feels stable is often the result of unseen competition, and it blurs the line between physics and philosophy, between the world as it is and the world as we're allowed to see it. So tonight, as you drift off to sleep, know this: reality is not static. It is filtered, selected, passed down. What you're seeing, what you're touching, what you're feeling is just one thin thread in a quantum web that once shimmered with possibility. Imagine waking up in a world where time runs backward, where you unspeak every word, walk in reverse through your memories, and inhale the air you just exhaled. In this world, cause follows effect. Ashes rise and become fire. Raindrops leap from puddles into the sky, and birth is just the final step before disappearing. It sounds like science fiction, but the foundations of modern physics suggest it might not be so strange. This is the realm of CPT symmetry, a deeply buried truth in the equations of the universe, and it leads to a radical possibility that somewhere beyond our reach, there could be a mirror universe made of antimatter, reflected in space, and running backward through time. To understand this, we begin with symmetry. In physics, symmetry is not about beauty, but about invariance. When the rules don't change, even when the world does, there are three fundamental symmetries that matter. C for charge, flipping the electrical charge of particles. P for parity, flipping spatial coordinates like looking into a mirror. T for time, running the process backward. Individually, these symmetries can be broken. The universe doesn't treat matter and antimatter equally. It doesn't look exactly the same when mirrored. And time, clearly, seems to have a direction. But when you combine all three, CPT, the theory says the laws of physics must stay the same, even if you flip all the charges, reverse all the spatial directions, and play time in reverse. The math still works. This is CPT symmetry, and it's a cornerstone of quantum field theory. It's not just an idea, it's a requirement for consistency in our deepest models of reality. But what does it mean physically? Some physicists have asked, if CPT symmetry holds perfectly, could there exist a CPT mirrored universe that balances our own? A cosmos where everything is flipped, antimatter instead of matter, left becomes right, time runs backward, not as a trick or illusion, but as its own reality. And here's the strangest part. If such a universe existed, and it began at the same Big Bang as ours, then time would flow outward from that point in both directions. From their perspective, we're the ones moving backward. They look at our world and see entropy increasing in reverse. Their coffee unmixes, their clocks run leftward, their ashes rise. But to them, it all feels normal, because entropy still increases, just from their point of view. In this theory, time isn't a river flowing one way. It's a symmetric explosion rippling outward in two directions. The Big Bang is not a beginning, but a middle, a mirror. This doesn't break physics. It completes it. Because if a CPT mirrored universe exists, it could solve some of our biggest puzzles, like the mystery of dark matter, the invisible mass that shapes galaxies but doesn't interact with light. Some researchers suggest that this backward universe, made of antimatter, could gravitationally interact with ours. We can't see it, but we can feel its pull. Two universes, back to back, bound by gravity, but blind to each other's light. One made of matter, the other antimatter. One flowing forward, the other backward. Both expanding, both increasing in entropy, both real. And maybe you've already brushed against it. In a particle that vanishes too early, in a ray of light that curves unexpectedly, in the silence between stars. This theory isn't proven, but it's not just imagination. It comes from the real mathematics of quantum field theory, from the equations that describe particles, energy, and space-time, and it forces us to ask, Is time truly one way, or is our experience of direction just a byproduct of how we live? We know that at the microscopic level, most physical laws are time-symmetric. They don't care whether you move forward or back. Only entropy, the spreading out of energy, gives us the illusion of direction. So maybe the arrow of time isn't drawn by the universe. Maybe it's drawn by us. We see time as movement from memory to unknown, from past to future, from cause to effect. But someone in the CPT mirrored universe might feel it all the same, just in reverse. Their history, their choices, their gravity, their lives. None less valid, just inverted. And what does that mean for you? It means that time, like everything else, may be relative, that your sense of before and after might be local to this branch of space-time, and that somewhere else, a version of reality runs in reverse. Not wrong, but balanced, a necessary reflection, a cosmic symmetry. And now, as you rest, feel time soften, not as a line, but as a wave. Reversible, elastic, shared, and next, we return to the edge of the unknowable, to the darkest object in the universe, and the deepest mystery in physics. What happens to information when it crosses the event horizon? Does it vanish, or does it find a way back? Because next, we face the paradox that tore physics in two. There is a place in the universe where gravity becomes infinite, where time slows, light bends, and the laws of physics begin to fray. A place so dense, so silent, that nothing, not even information, can escape. Or can it? This is the mystery of the black hole information paradox. A puzzle so deep it shakes the foundations of quantum mechanics, general relativity, and our very idea of what can be known. Let's start with what a black hole is. A black hole forms when a massive star collapses under its own gravity. The core contracts into a single point, a singularity, surrounded by an invisible boundary called the event horizon. Once something crosses that boundary, it can never return. Not a spacecraft, not a photon, not a whisper. It's gone. At least, that's what general relativity says, but quantum mechanics tells a different story. In the 1970s, Stephen Hawking combined quantum theory with black hole physics and discovered something strange. Black holes aren't completely black. They radiate tiny amounts of energy over time, now called Hawking radiation. This radiation is thermal, featureless, and random. And here's the problem. If a black hole emits this radiation, it slowly evaporates, it shrinks, and eventually it disappears, leaving nothing behind. But what about everything that fell into it? The planets, the particles, the light, the information. In physics, information means more than just data. It means the specific arrangement of particles and energy, the blueprint of how things were. And quantum mechanics insists that information is never truly lost. Even if it's scrambled or hidden, it still exists. That's the principle of unitarity. And it's sacred in quantum theory. So if a black hole evaporates into random heat, with no trace of what it once contained, that violates unitarity. It means information has been destroyed. And if that's true, then quantum mechanics breaks. But if information doesn't disappear, then where does it go? How can the black hole emit it if Hawking radiation is purely thermal? This is the paradox. If black holes destroy information, quantum physics fails. If black holes preserve information, then general relativity can't be the full picture. Something is missing, and no one knows what it is. Over the years, physicists have proposed many possible solutions. Some believe the information is stored in the event horizon itself, encoded on the surface, like a hologram. This leads to the holographic principle. which says that all the information inside a volume of space can be described by the information on its boundary. Others propose that information escapes gradually, subtly encoded in Hawking radiation through quantum entanglement. But that requires the black hole to remember everything it's absorbed, and somehow imprint that memory on random particles of light. Still, others suggest that black holes leave behind a remnant, a tiny leftover object that holds all the data. But this leads to new complications, infinite possibilities, unbounded energies, mathematical nightmares. And then there's the most radical idea of all, that space and time themselves are not fundamental. That reality is built from information, and black holes are just places where that information changes form, not destroyed, not lost, just restructured. But no theory has resolved the paradox completely. We have hints, we have math, we have ideas, but no final answer. The paradox remains, like a wound in the fabric of our theories, a place where two great laws contradict each other. General relativity, predicting inevitable collapse, smooth space-time, and silence. Quantum mechanics, demanding reversibility, uncertainty, and memory. Both are brilliant, both are proven, but together they disagree. And so the black hole becomes a riddle, not just in space, but in thought, a test of our understanding, a mirror of our limits. What does this mean for you? It means that even the most powerful theories we hold can fall silent at the edge of a mystery. That knowledge isn't always clarity. Sometimes it's the outline of a question you weren't meant to answer. And yet, we keep asking, we keep staring into the dark and wondering what's behind it, not to conquer it, but to feel it, to know, even briefly, that the universe is stranger than we can hold, and that we are part of that strangeness. Tonight, as you drift further into stillness, imagine this: a black hole shrinking, quietly, light by light, until it's gone, but not empty, still echoing with everything it once contained, still humming with a memory of form.